Welcome to CS-412 Software Security. This is the speedrun of OXOB testing, and today we're going to talk about advanced fuzzing. The learning goals for today are as follows. First, we want to be able to discuss trade-offs for fuzzing binaries, especially if you look at costly instrumentation versus black box fuzzing. Know the binary instrumentation techniques, and especially distinguish between dynamic instrumentation and static instrumentation, and know the different trade-offs. Understand the complexities of library testing, and especially the LLVM LibFuzzer implementation of library testing. And then discuss limitations of automatic driver constructions for libraries. Today we're going to focus on three different topics on advanced fuzzing, and especially their challenges. You've learned so far mostly about regular standard gray box fuzzing, where you target an individual binary, and different kind of instrumentations where you can get sanitization as an oracle to signal that a crash has actually happened or that a bug has been triggered. Today we'll focus on three different orthogonal areas: fuzzing binaries, as in without previous instrumentation; fuzzing libraries by writing custom fuzz drivers as unit tests; and then by fuzzing libraries automatically. And we're going to focus on these three parts one after the other. Let's start with fuzzing binaries. And for fuzzing binaries, we have to kind of open this black box and figure out how we can get sufficient amount of information from running this arbitrary binary that does not come with the additional instrumentation. In the past 2 weeks or lectures, we've actually looked at fuzzing binaries and our key instrument or fuzzing programs, and our key approach has been to compile these binaries with instrumentation. Now, if you're fuzzing binaries, a regular binary usually comes without coverage instrumentation. And if we don't have coverage, the only thing we can do is fall back to black box fuzzing or to leverage some alternate forms of coverage. The big drawback of black box fuzzing is that this fuzzing requires one-shot hits. As in, we generate an input, and then with this input, we just try to make sure to hit a given bug. And any input is independent from all other inputs, right? So we are creating an input from scratch, and we're trying this one-shot effort to see if we can actually trigger a bug. An alternate solution to fuzzing binaries is to rewrite those binaries to add coverage instrumentation, so that we can get feedback on it and we can make input generation dependent on previous inputs. So if a previous input triggered interesting coverage, we can use this input to further mutate it and therefore kind of search in the nearby area for given bugs or vulnerabilities. Now, binary instrumentation comes at a cost. And the key takeaway here is that some performance impact is still better than black box fuzzing. So it really depends on what you're looking for. But generally, some performance impact is okay because we get much better quality for the input generation, right? So there's a quality versus performance trade-off. And similar as with sanitization, some performance impact is usually okay. When rewriting binaries or when fuzzing binaries, the first approach is just to do black box fuzzing. And if we don't have an excellent input generation for this black box, then this is usually not recommended. The second approach is to rewrite binaries dynamically, as in during the execution of the binary, we will translate the target at runtime as it is executing. This comes at a terrible performance overhead of 10 to 100x or maybe even 1000x lower. And this is because of the additional overhead of the binary rewriting and the interposition of all the indirect control flow transfers. This is done through example AFL QEMU and works right out of the box. So you don't have to do anything to the binary or with the binary. But it comes at this overhead, right? So you're paying a 10 to 100 or 1000x slowdown for this instrumentation, and it is somewhat limited in the overhead, right? So this is a very hard trade-off. This may work in some cases, but this is likely not a general, not the best approach for all the binaries. Now the second approach, and this is where we'll go a bit more into detail, is to rewrite statically. This means that we develop a static analysis to rewrite the binary using a complex analysis, but then we get a lot better performance, right? So this requires a little bit of work ahead of time, a complex analysis and a complex system, but then you get much better performance because you get the same performance as if the binary was originally instrumented with coverage instrumentation, right? So you're not paying the dynamic binary translation tax. So dynamic binary translation comes at a cost, but it has a low barrier to entry and it works for all the binaries. Whereas static rewriting requires additional complexity for the rewriting, but then comes at a huge performance boost. Now, why is static rewriting hard? And we'll take a little bit of a detour into discussing challenges in dynamic binary or static binary rewriting. If you look at the code here, right, these three assembly instructions, we've got a move, we've got a decrement of a register and then a jump if the RBX is not 0, right? So simply adding code in between breaks the target. If you would simply add all the new code in there, this jump not 0 would branch into some other instructions that would have been added. So what we can do is we can find these references and adjust them, and we actually must find all the references and adjust them. So this may be easy for direct jumps, like this jump not 0, where the target is actually encoded in the instruction itself, but it is much harder for indirect jumps. For example, if it jumps through a register, or if we return, or if we jump through a memory address, right? And the big issue here is like that we would need to adjust the original pointers. Now the difficulty is that scalars and references are indistinguishable. We would have to adjust all the pointers to the address space that points to the code region. But we don't know if something is a pointer or simply an integer value, because in assembly, scalars and references are simply indistinguishable. Getting a single one wrong will break the target. Now, if we look at this move instruction here, we are writing this value into a memory address, right? And here the issue is that, this could either be an assignment of bar, like an address, into this like a target value into this variable, right? Into the variable foo. So we could be updating the variable foo and turning this into a pointer, right? So foo becomes a reference to bar. Or it could be that the foo is a long value and we're actually assigning a concrete value to it, right? So this is indistinguishable, and this is indistinguishable at the assembly level. Now, what we developed in a couple of years ago is retrowrite, which is a system for static binary instrumentation for PIC code. This is code that is position independent, that assumes that symbolized assembly files are easy to instrument. And using retrowrite, you can take a binary, you can lift it into symbolized assembly that can be instrumented, and then in addition to that, we implement coverage tracking and binary ASAN on top of this symbolized assembly file. Our key finding is that position independent code allows us to recover a sufficient amount of information to carry out this necessary instrumentation. So PIC code, position independent code, is code that can be loaded at any address, and this is required for ASLR or shared libraries. So in PIC code, you cannot use hard-coded static addresses and must use relative addressing instead. And this allows us to recover all the necessary information if something is a pointer or a scalar. So on x86-64, PIC position independent code leverages RIP relative addressing. So we have this RIP relative address, and we know that this is actually a code pointer. So we can distinguish references from constants. If it's RIP relative, it's a reference. Everything else is a constant. And this allows us to do the necessary symbolization, right? So we start with the assembly code at the lower right, and symbolization replaces all the references with assembler labels, right? So in the very first step, right, our analysis, the first round of the analysis, replaces all the relative jumps and calls. And this is, for example, a jump not 0 in this example, or the call OX lead, right? So we replace OX lead with a call to function 1, and jump not 0 with a jump loop 1, and then we insert the label loop 1. As a second step, we analyze RIP relative addresses and check if this is pointing to the code region or the data region or whatnot. And then we insert the individual labels in the different regions. This could be a code region or a data region. Here for this LIA, RIP plus OX1234, we detected this as a reference to the data region, and we replace this with a variable to, for example, data1, right? Then we do more data relocations. These are actual relocations to, for example, other libraries or whatnot. And now, after we have completed all of these changes, this is code that can easily be reassembled, and it can also be changed, right? So now we can perfectly add new code somewhere in the middle to carry out the necessary instrumentation, and this can be perfectly reassembled later. So binary rewriting allows adding coverage and sanitizer instrumentation. Retrowrite, as we discussed, offers a tool, or is a tool for static binary rewriting that exploits the information from relocations. Performance is close to native instrumentation for coverage and about 30% higher for ASAN. There's a loss in precision for ASAN due to the lack of metadata for stacks and globals and whatnot. The alternative, dynamic binary rewriting, is implemented through QEMU or Valgrind, which offer dynamic binary rewriting and are implemented on top of AFL. But they come with a 10 to 1000x performance overhead. And they've got the same loss in precision for any kind of address sanitization, right? But the key advantage is that for dynamic binary rewriting, this works for any binary, whereas retrowrite requires the binary to be a pick binary, right? A position independent code binary. So that's the trade-off. But it comes at a much higher and much better performance. So you've got three options. If you have a binary, you can fuzz a native binary as a black box. If you have extremely good information about what input is expected, so you can have good input generation, then this may actually work. You can instrument through retrowrite if it is a pick binary, or use QEMU Valgrind as a last resort, right? So this allows you to fuzz binaries that are not intended to be fuzzed, right? That are, for example, just native binaries without debugging information or whatnot that you find somewhere and that you would like to target. Cool, so far so good. Let's now talk about libraries. And in particular, we will look at LibFuzzer, which allows you to target specific libraries and specific library functionality by creating fuzzing stubs. So far, we have fuzzed programs, and we started from the main function in the program and then kind of dove into the different parts. There's too much reachable functionality and code bloat in libraries usually, and it's very hard to figure out what functions should actually be tested in a library. And similarly, not all functionality in a library is actually exposed, right? So a library may only export a very limited API and require a particular sequence of calls into the library to build up the necessary state. It's also hard to focus on a particular use case for a library. We'll therefore look at LibFuzzer, which is a tool that allows us to customize the fuzzing process to a particular target. So LibFuzzer is an in-process, coverage-guided, evolutionary fuzzing engine and enables library testing following a unit test approach. So you, as the developer, you will write the unit test, construct the library API, connect the different parts, and then you can go fuzz, right? So in LibFuzzer, you write individual unit tests. So it enables a developer-guided approach to custom tailor the fuzzing. The developer is responsible to connect the different parts and to make sure that the library is initialized correctly. So the developer cycles are used to set up, tailor, guide the fuzzing process, set up the necessary state, and then the fuzzer goes explore this state space. LibFuzzer provides fuzz. This is a fuzz input of a certain length, and the developer is assumed to know the target application, sets up the state, and feeds the fuzz data into the right parts. LibFuzzer uses then coverage feedback to explore the program and runs in process for speed. So the philosophy is quite different, right? Here the idea is that LibFuzzer will stop after the first discovered crash and simply report, we found a crash, we're done, and it's all good, right? So this is a slightly different philosophy from AFL, which tries to find as many bugs as possible, right? So it's a trade-off. LibFuzzer is more focused as a developer tool, whereas AFL just tries to find bugs broadly across many different targets. In LibFuzzer, you write a single unit test as a LLVM-fuzzer test1 input, and then you get an uint8 of the data array and a size. And then you can actually do something interesting with your API, with the data and the size. And then you return 0 when you're done. So this is one test where you get fuzz input, and then the fuzzer will use coverage feedback in the function, do something interesting with my API to mutate the data and the size being passed. Right? So that's the fuzzer then explores automatically this function that you are targeting and creates many different unit tests, test inputs for this target. So there's a couple of things you need to consider when you're writing a fuzzing stub. It needs to be stateless, right? So you cannot change any global state or depend on any global state across calls, right? So you want to, the fuzzing engine will execute the stub many times. If you need to set up a particular set of state, you need to do this in the fuzzing stub itself or in specific setup functions. And you also need to tear down the state by, for example, freeing the necessary functions. It needs to be resilient. Your stub needs to be resilient. It must tolerate any input, empty, huge, malformed, whatnot. And it must be continuous, right? You cannot just call exit on bad input because this would stop the fuzzing process. It also needs to be contiguous, right? There's a single entry in exit, and the threads must join before the round completes, so the fuzzing process can actually continue with the next round. And last but not least, it needs to be fast. The rounds should be fast and without unnecessary computations. You want to focus on calling the actual library functions and not just spend all your time in the fuzzing process itself, right? In the unit test itself. The key idea here is that narrow targets will allow deeper state exploration than wide broad targets. So you want to create a specific functionality, right? One example for a simple LibFuzzer, or how LibFuzzer works, is we can use it to generate an input string, right? To quickly query the solver to find CS-412 by setting a couple of bit flags, right? And we only crash if all the branches have been fuzzed in this example, and we then use coverage feedback in this example and the target to detect that, hey, there's new branches being found, and bits are being set until the fuzzer will very quickly discover these 127 individual paths, and each path will be set individually. It's quite cool, and LibFuzzer works extremely well for these targets. But ideally, you should be calling different library functions here, not just follow this example. So fuzzing stub sets up interesting states and invokes these API functions. It's very similar to writing a unit test. And then you compile your stub and your library, of course. Your library you would compile with coverage instrumentation and with address sanitization, and the library you compile with sanitization. And then fsanitize equal fuzzer and address. And the equal fsanitize equal fuzzer will turn your LLVM fuzzer test1 input into an actual fuzzing stub that then calls the fuzzer. You compile with coverage instrumentation, consider the environment, length of the input, number of parallel jobs, and whatnot, and then you create a starting corpus using some well-known good and bad files for the fuzzer. And then you can go fuzz with /fuzzer, corporate directory, and then it just goes and starts doing weird mutations. As always, mutations are key to the exploration, and LibFuzzer has the same or a very similar set of mutations compared to AFL. It can delete individual bit, byte, bytes, insert, change, or shuffle them, splice, combine two different seeds, inject dictionary tokens, mutate data types of integers and strings and whatnot, and thereby create new and different inputs based on coverage, right? And then if an input creates and finds triggers new coverage or interesting coverage, it can then be used further for later mutation. What LibFuzzer also supports, and this is an interesting extension, is that you can do custom mutations. Custom mutators can leverage this local information to improve the mutation. Right? So it's a custom tailored input, goes beyond the parser if you want to go into a very complex area. And here you can use insider knowledge to trigger interesting corner cases. Right? So the input is the data and lengths, similar to before, and output is data and lengths, which must be shorter than what came in. Right? So you return the lengths of the input data that you actually. So you take in random data in this data plus size in place, and you change it and you return it. You return the new size, which makes this somewhat interesting. And given the same seed, it should produce the same mutation. This allows you to, for example, fix checksums in an image format, or clear out checksums, set specific flags if you need to, and whatnot. Right? So this allows you to generalize and customize the mutator to make sure that, hey, it actually satisfies certain criteria that you know must hold true. LibFuzzer allows very different coverage feedback, and you can select the coverage that you are interested in. Coverage, as you know, is essential for effective fuzzing, and it guides the mutation. LibFuzzer supports a very diverse set of coverage. You can just do Boolean edge coverage, like as an edge has been triggered or not. You can count how many times an edge has been covered with like the second flag with 8-bit counters. You can trace indirect calls. You can trace execution paths and whatnot, right? So you can be more and more fine-grained. So if you have any recent clang, you just do fsanitize equal fuzzer, and then coverage will be automatically added, and this is going to be fine. Now, one thing that you will notice is that corpora grow very quickly and over time. So every now and then you have to reduce the fuzzing corpus to increase its effectiveness, right? If you have this large and big corpus that has accumulated over time, you can either sort it into subcorpora by functionality or whatnot, or you can prune and merge inputs, right, to make sure that you have a minimal corpus for the next iteration of the fuzzing process, right? And here you want to play this trade-off between having an efficient small corpus that triggers all the functionality in as diverse ways as possible, but also not having too many input files to iterate over, because the fuzzer only has finite energy and it takes a lot of time to go through all the inputs. And especially if the inputs are too similar, or one is a superset of another, it may not be worth it to do the same work twice. Dictionary synthesis, right? Many targets speak a given language, so knowing the tokens actually will improve the mutation, and the fuzzer can then inject domain-specific keywords into the input. So you're giving the fuzzer additional power to create reasonable inputs by speaking the target language. The mutations are then more likely to trigger new behavior. So this gives you a massive speed up, as random bit flips will take quite a while to produce specific keywords, and you can simply insert the keyword as needed. You can create dictionaries manually or based on execution feedback, right? So you can just pass a dict file, or you can just use a trace comp and use whatever is being used in comparison, using some magic functions that will dump these targets in the dictionary automatically. Cool. This allows you to write unit tests for libraries, and actually use this unit test to then test the libraries. But now we want to go a bit further, right? And actually automatically analyze the API of a given library. As you may have thought or considered, fuzzing libraries is hard. So you cannot run them as standalone programs. There's no dependency information across API. And for writing LibFuzzer stubs, we need a developer that actually knows the library fairly well. We would like to do this automatically, and even without dependency information across the API. Right? For example, you can only read from a file after opening it, or you can no longer write to a file after closing it. So there's a lot of dependency information between API calls that is maybe not necessarily explicit in the library itself. So the goal for library fuzzing is to invoke the API in the right order with the right arguments, and then decide where to feed in the fuzz input. So there's a need to build complex shared state to pass between calls. For example, if I look at OpenSSL, there's a very complex struct that is being created initially and then being filled with additional information through a lot of individual calls into the library. If the calls are not in the right order, it will simply fail. And this is a bug in the fuzz driver and not a bug in the library. So we have to reduce these false positives that would then trigger these wrong faults. So in FuzzGen, we are trying to learn the API. So we have a target library. We try to infer using a whole system analysis how the API is actually being used by analyzing the library consumers. Our key intuition is that, hey, if we do have a library as our target, we will find a certain amount of consumers of programs that are actually using the library, and then we analyze how these programs use the library and abstract this into an abstract API dependence graph, right? So this API dependence graph allows us to figure out how the different parts are interacting with each other, and then based on this API dependence graph, we can then create new fuzzing stubs by just doing a random walk through this graph. The first step is to infer the necessary API. So we discover all the declared functions in the library by parsing the header files. Then we analyze which of these functions are used in the system by looking at a set of target programs. And then we intersect the two sets to discover the used library functions. Anything that is exported by the library and is actually used in a program that is not the library itself is considered part of the exported library functionality. Now, based on this exported library functionality, we need to figure out the dependencies between any of these entries in a set. So we want to abstract the layout from a single library consumer. So we take a target program that uses our library and then figure out the control and data dependencies by analyzing the target program. The output should be a directed graph of API calls generated from the control flow graph. And here the idea is that we start from the control flow graph, we abstract it, and we then generate this abstract API dependence graph. So on the right hand side you see the control flow graph of a target program, and this is actually a unit test for libopus, and you can see that this is rather complex. And there's only a few calls to libopus. There's opus decoder create, opus decoder control, opus decode, opus decoder destroy, get bandwidth, number channels, and whatnot. As we summarize this in our analysis, we remove all the nodes that are not API dependent, and we can collapse this to the API dependence graph that you see on the left hand side. Right? If we remove all the nodes that are not API dependent, we can create the API dependence graph that you see on the left hand side. In addition to that, we track the data flow of concrete values. And for example, if in the get number channels or get bandwidth that uses specific tokens, as in fixed numbers, we can actually use those and detect those as hard values. So the fuzzer would not inject wrong fuzz input in those targets. Now we have an abstract API dependence graph for each consumer. We now coalesce all these dependence graphs into a single one used for fuzzing. This requires at least one common node, and then we just start merging based on common nodes and create a super graph that kind of combines all the information across all the different consumers. For the argument ranges that I quickly mentioned before, right? Not all arguments should be fuzzed, and we need to have some understanding of some of the target functions of what to fuzz and how to fuzz it. And for that, we do this data flow analysis and backward slice to see if any constant or fixed values flow into these arguments. And this allows us to detect dependencies across arguments and, for example, fix them based on static values. Right? These constraints allow us to reduce the false positives and then decide that, for example, for this mem copy, we would feed in fuzz data in source, and we would keep the constraint that destination needs to be at least large enough for size. Right? If we detect that this is actually being checked right before. So this allows us to tie the different parts together. Now, as we create fuzzing stubs, we translate this abstract API dependence graph into C++ statements by doing a random walk through the abstract API dependence graph. The fuzzer then explores the valid path. So we make sure to preserve the order of every API call, group based on topology, and then invoke every function exactly once to make sure that this is somewhat efficient. We evaluated our target on Debian and Android on different kind of codec libraries used with AZAN, and did 24-hour experiments, and this found 16 bugs and 6 CVEs that we reported to Google and have been fixed on the Android phones. So FuzzGen presents whole system analysis that infers API interactions and allows us to automatically synthesize high entropy LibFuzzer stubs. It constructs a complex program state and achieves very high code coverage. The implementation is roughly 20,000 lines in C++ on top of LLVM. But it was fairly efficient in finding bugs. So let's recap our discussion on advanced fuzzing and 3 different fuzzing niches. Well, first off, fuzzing binaries is challenging. There's a trade-off between instrumentation and information, and you need to be aware what this trade-off and the complexity is. Black box fuzzing can be efficient if you can create good high-quality input. Otherwise, you just require some form of coverage instrumentation. This can be done through static binary analysis if the target is amenable for instrumentation and pick code, or you can always fall back to dynamic binary rewriting, which comes at a terrible overhead but gives you coverage information. Generic fuzzers don't scale to complex APIs and very complex programs. That's why you need to create smaller targets that allow you to slice a particular aspect of the target. LibFuzzer is the target that applies unit test principles to fuzzing, and it allows the developers or the domain expert to create a fuzzing stub and then encode the constraints between the individual API calls. The fuzzer then explores this fuzzing stub. Here you spend a few cycles of the developer to set up the fuzzing process, and then LibFuzzer automatically explores the deep state of the fuzzer. With FuzzGen, we've shown that there's automatic approaches that try to infer the API dependence graph and try to automatically create fuzzing stubs that you will likely have to slightly adjust in the end to make sure they run. And this is actually an ongoing field of research, right? This automated API analysis, the extraction of these dependencies and the stub creation are very interesting targets of research to make fuzzing even more efficient going forward. So this lecture concludes the fuzzing and testing section of the class. We've talked about generic testing for using static analysis, dynamic analysis, and automated testing using fuzzing in quite a bit of depth. We've also discussed sanitization, how to detect if a bug has been triggered, and today we discussed some of the advanced testing techniques. This is all that I had for fuzzing or automated testing, and I'll see you next week or next time for additional information on a couple of case studies. Thank you.